All right, Calc 2 students, welcome back to our online classroom. I posted some information on our Foxtel site. Most important thing is that I'm going to be available on Zoom on the link provided at Foxtel every Monday, Wednesday, Friday from 8:30 to 10. You can participate or not as you feel you need. And mostly what I'm going to do is answer questions. Most of those days, there will be an assignment due, and maybe you'll have some questions. I anticipate some of you will. And so I'll be here. If no one comes to visit me, that's okay. I won't get lonely. But if you have a question, by all means, log in. You can count on me being there 8:30 to 10 o'clock, Monday, Wednesday, Friday. You can also reach me by email, and if you have a question comes up not during those irregular hours, just shoot me an email and I'll help you out as best I can. Also, Math Lab is supposed to be operating on Zoom in its traditional hours, so Sunday through Thursday, 5 to 9. It's still closing early on Wednesday, even though there's no chapel on campus. I think because that's the way the student schedule works out. All right. So I posted a video for today's class. It was on alternating series that alternate in signs. I hope you were able to watch that and connect with it and work through the problems with Nick, the problems he chose to do. And then just this morning, I posted an assignment, which will be due Wednesday, the usual time, midnight. I've changed the controls on the Pearson homework, so you actually have unlimited tries. So get them right. There's no penalty for trying until you get it right. All right, we basically have covered all the material of chapter 10, all the material that we're going to cover. There's a few things in there that we haven't spent time on. I thought before we move on to the next chapter, chapter 11, which is still about infinite series, a little different take on it, I thought I'd just take a minute to summarize all the things we learned in chapter 10. I've written them on the board here. Basically, you can see we have discovered 10 different ways we can analyze a series. Most of those are tests. 3 of them are not. I'll talk about those in just a minute. And when I say analyze a series, we want to know, does it converge or does it diverge? If it converges, we might wonder what value does it converge to. Sometimes we can decide that. Most of the time we can't. We'll do better at that in the next chapter. So mostly, with an exception I'll talk about in just a minute, what we're looking at is, does it converge or does it diverge? And can we prove it? Can we find the test that verifies it? So I'm going to summarize these 10 ways we know. And then I'm going to pick some problems sort of semi at random from the review problems at the end of chapter 10. And I'll talk through, how we decide. Having 10 things gives us a lot of power, but it also requires us to really understand how they operate and to know which one is a good one to use when we're confronted with series whose behavior we don't know. All right, so quickly. The first one is the definition, the limit of the sequence of partial sums. And notice I wrote rare. We've pretty much gotten all the information out of that we're going to get. There was if you remember, the telescoping series that we could use there. And then there was a very important case, geometric series. That's the second one. Notice I've circled those first 2 in red, because if we can settle the issue there, we actually can find the sum. We know how to sum a geometric series, and the very definition of an infinite series is this limit. If we can find the limit, then of course we know the sum. Other than that, these other guys, all 8 of them, all they do is tell us, does it converge or does it diverge? The value is a mystery, at least for a little while. All right, so notice I've also separated them into kind of 3 categories, the definition here, and then we have some specific series that aren't really tests. Geometric series, we know when they converge, we know when they diverge, we know 100% of the time, and then we have the special case P series. And we know then that a p-series converges if and only if p is bigger than 1. If it's less than or equal to 1, it diverges. So we have specific series here, and then we launch our tests, the divergence, the integral, 2 comparison tests, ratio, the root test, and finally, the alternating series test. Okay, I suggest that you make a list about like this, and you might want to add detail to it. For example, how do we run the test? Let me just give you a really quick example. Which one? The ratio test. We calculate a limit as n goes to infinity, the n plus first term divided by the nth term. If the ratio test is going to work for us, and there is the possibility on any given series that none of these, that is, there might only be one test that works, so we have to kind of find it. If it's going to work here, we're going to be able to find this limit. We're going to have the value L, and then we know if L is less than 1, it converges. If L is greater than 1, it diverges. If L equals 1, it's inconclusive. We don't know. We need to find another test. But at least we know we can mark 1 off the list. Okay, so every test 4 through 10 have these conditions, that how we run the test and how we interpret the result. So you should start formulating in your mind, and maybe even on paper, think about a 3x5 note card maybe, the best way for you to get that information down. And you really need to pay attention because they're all similar, but they're all a little bit different. So on the board, with the exception of the ratio test, I haven't written the details out. Let me get out of the way of the ratio so you can see it. All right, so what I want to do next is, like I said, I'll just pick some problems sort of semi at random. What I mean semi is there's probably some super difficult ones, and those are really fun to try to solve. They test our skills. But I'm not going to pick those. I'm going to pick one that will be more similar to what you might see on the exam. Scheduled for next week, more on that later. So I'm going to pause the video while I change the board, and then I'll be right back. All right, welcome back. As I said before, these are chosen out of the Chapter 10 review problems, which you can find on page 706. And I chose the very first one, number 42. So sum from 1 to infinity k over k to the 5/2 plus 1. Okay, so how do we think about this? You cover up the plus 1, and the plus 1 becomes insignificant as k goes to infinity, and it does go to infinity. Then you can see that this looks an awful lot like a p-series. That is, we have k to the first on top, and we have k to the 5/2 on the bottom, which that is equal to, if I cancel that 1 out, I have 1 over k to the 3/2. So if we cover up the plus 1, we can't ignore it, but we do know that it becomes insignificant as k goes to infinity. So when you look at that, you should see the basics of a p-series. And by subtracting these, we find the value of p. So I'm going to do the limit comparison with the p-series. And hopefully, this p-series converges. Summation 1 over k to the 3/2 converges. So if we get a finite, positive finite value for the limit from the limit comparison, then we'll have the same conclusion. So limit comparison. We're going to calculate L, the limit as k goes to infinity. The unknown series, we always put it on top, the formula for it. And the known one we put on the bottom. So we've seen this a lot in chapter 10. We have a fraction divided by a fraction. I've encouraged you to maybe skip this step and just flip this one over and multiply. I wrote it out here. Maybe in the future, when we need it, we'll do that. So I have k over k to the 5/2 plus 1 times, and then invert and multiply. So in the numerator, k to the 3/2 times k is k to the 5/2. No coincidence that that's the same power as we had. Okay. Because of the fractional power, those are not polynomials. But it's not hard to believe that the limit's going to work like it did for rational functions, a polynomial divided by a polynomial. If we could think of degree, we don't really define it for fractional powers, but the numerator and the top, they have the same one, 5/2. Now, officially, we could do L'Hopital's rule here. Because the derivative of the top is exactly the same as the derivative of the bottom. So you apply L'Hopital's rule once, and the function turns into the function 1. The derivative divided by the derivative, those are the same, so it equals 1. So thinking about that, we can get the limit as 1. I don't think we need to calculate the derivative. It'll be the same. We can see that because the derivative of 1 is 0. It's going to go away. And because this is positive and finite, this is what I was talking about earlier before. We need to know how we interpret the limit comparison. It means that the series we didn't know behaves as the same as the one we chose, which is convergence. So this series converges. Again, we don't know the sum. We don't have any way to determine the sum. We just have to be content with deciding what it does, converge or diverge. All right, if you have questions, I'll see you on Wednesday morning about that problem. I have another one to do, and we'll do another one or two after that. So here's another one, number 58, same page. There are a variety of tests we could use here. I'm going to use the ratio test. You could also use the integral test, and maybe there are others. So use the ratio test. So we're going to calculate L, the limit, k goes to infinity. Notice this is one of those rare ones that's not a fraction, at least the way it's written here. So we'll just take the k plus first term divided by the kth term. So we need to find that limit. The limit of a product is the product of the limits, right? Remember those days? So let's separate this into the polynomials. Some of you maybe can see past this step, don't need to write it out. Times the limit. If both of these limits exist, we'll figure out if they do. Distribute that minus sign. So the first limit here, what is it? I hear that, 1. The second one, the limit as k goes to infinity. Let's use the properties of exponents to break this into the product. Right? And then notice the exponentials cancel, and we get e to the minus 1, which is 1 over e. And that number is less than 1, which is important for the ratio test. So we calculate the limit. we get a number that's less than 1. This number, the actual number is meaningless. The only thing that matters is which side of 1 does it land on, and this lands on the low side. Therefore, this series converges. We didn't analyze it very closely. If this k weren't here, it would just be a geometric series and things would be nice and easy. But with the k there, it's not geometric, but there's a thing we can do, and it's not so super complicated. It might be easy to forget these parentheses. And if you do, the e to the minus k's cancel, but you'll have a e to the plus 1, which is e, which unfortunately falls on the other side of 1, and you would make the wrong conclusion. So be careful distributing that minus sign out. Very important to get a minus sign. All right, I'm going to pause you. I'll pick a couple more, and I'll be right. All right, I've picked out a couple more. Start with number 63. I picked out 2 that require, maybe requires too strong of a word, that we can use a different test. So the 4 problems we'll work through, we'll use 4 different tests. But as you saw, there were, what, 7 of them? So it's not going to be exhaustive, but it'll give us an idea. So on 63, again, I do like we did maybe on the one I wrote here before, that is, as k goes to infinity, that 2 becomes insignificant. When I look at that, I see a geometric series. Cover the 2 up. So here's the geometric series I see. I'll write it in kind of standard geometric form. Doesn't really matter where k starts, but we'll write it. And that geometric series, r equals 1 over e, which is less than 1, so it converges. We could find what it converges to, but we don't need to know. It wouldn't tell us what this thing converges to. All right, so I'm going to use the ordinary comparison test. And then maybe I'll use the limit comparison test, just so you can see them side by side. The limit comparison is, when it works, is easier to do. Remember the comparison test, we have to prove an inequality. And we don't have a lot of tools to do that. We don't talk about it very much. This one's going to be easy, so no problem. For the limit comparison, we calculate a limit, and we're, can I say, expert at that. We put a lot of effort in to how to compute limits. So usually the limit comparison is preferable to the ordinary comparison. Now there are times where the limit comparison won't work, where the limit that we need doesn't exist, but the comparison test will. To my mind, that happens when there's sine or cosine involved, because as you know, the limit of cosine or sine doesn't exist as k goes to infinity. So there's no sine or cosine here, so we'll do it both ways, comparison test. So this is pretty trivially true. E to the k is smaller than 2 plus e to the k. This is exactly 2 bigger than that. If I reciprocate, flip over expressions from an inequality, the sign of the inequality changes. So I'm going to do that by flipping these guys around. So we're going to reciprocate, and I'm going to move this guy to the left because now he's the smallest. And finally, multiply by 3. You can multiply an inequality by a positive number, and the inequality stays the same. Of course, everything is positive here. So I've shown that the terms of this unknown series, just the terms, are 1-to-1 smaller than the corresponding terms of the series whose behavior we know, and in particular, we know it converges. So if I add up all of these from 0 to infinity, I get a finite number, and these are all smaller. They're all positive, so it's not going to minus infinity or anything weird like that. This is true for all values of k from 0 to infinity. So since these guys, all of them add up to a finite number, so does this. So since this converges, our original one, let's make an arrow up here, this guy converges. And we know because of this inequality, it's going to converge to a number smaller than what this one does, and we can find that one, but we're not worried about that. Now, limit comparison. By the way, we don't need two tests. I'm just showing you, I'm comparing them, so to speak, side by side. There you go. I'm going to use the same one. Remember limit comparison, we still have to dream up a comparative series. I'm going to use the same one. We calculate the limit. The series we do know goes on the bottom. And the series we don't know goes on the top. Notice those 3's cancel right off the bat. And if I divide those fractions, again, invert and multiply, I get e to the k over 2 plus e to the k. What's that limit? Check my algebra. Again, like the one we did a little bit ago, the derivative, both of those go to infinity, the exponential growth, but they have the same derivative. So you apply L'Hopital's rule once, and we get 1. The limit is 1. This is the limit comparison. Getting a positive finite value means this series behaves the same as that one. Well, we know this one converges, so that one converges. Okay? Now, never ever, like on an exam or in a physics class, we don't need to prove it converges 2 ways. I did it 2 ways just so you can get a feel for how the comparison test, establishing inequalities, compares to the limit comparison, computing the limit. And my guess is most of you feel better about limit comparison. There are some cases, like I mentioned, sine or cosine are involved, probably, and we think that that a comparison, one or the other, is the right test to use. We may have to go back and prove the inequality. Number 45. Converge or diverge. Take a minute to look at it. So what I notice here is that as k goes to infinity, I have a 4th degree polynomial divided by a 4th degree polynomial. It's like I said over here, we're experts at limits. That's what we believe. And when I see a 4th degree polynomial divided by a 4th degree, then I know what the limit is going to be. As k goes to infinity, it's just going to be the ratio of those leading coefficients. 2/3. 2/3 is not 0. Again, this is the formula that generates the terms. If it does not go to 0, that series diverges. Okay? And there are 4 examples. I want to do one more thing. It could be that the calculus professor did this on one of his lecture videos. I can't remember, but I want to talk, remember we've identified a particular series with a name, the harmonic series. And what we know about the harmonic series actually, I just realized I have a meeting coming up and I'm going to be late. So we'll talk about the harmonic series, what I want to say here at some later date. So This is a summary between chapters 10 and 11. So before Wednesday at 8:30, I'll post specific instructions for Wednesday's class. It will include this video, and it will also include a reference to the next material in the textbook, which will be the calculus professor's videos on what for us is chapter 11. For him, it may be chapter 9 or 10. We'll see. So that concludes this video. And if you have any questions, shoot me an email. Otherwise, happy calculus problem solving.